Good afternoon, everyone. Thank you for coming. So we have a special guest today. We have Irina. It feels like UTS all over again, but it's a new part of UTS. So Irina is now lecturer and researcher in UTS. She did her PhD in Sydney Uni and graduated, I think, 2012. And then she did postdoc in Sydney Uni and Amolf. Yes,
and Amolf in Amsterdam.
Yeah, in Amsterdam. And then she joined the Imperial College. So it seems like she followed Ned. We just spoke about that. Probably the next stop is UNSW. Push you. So she was in the Imperial College in London for 1 or 2 years.
2 years.
Yes. And then she got a permanent position in UTS in the end of last year. So well done on that.
Thank you.
And she worked in special on advanced material, or special material, like special because of Angus and advanced because UNSW put advanced on everything. And she will speak with us, I think mainly on perovskite? Oh, yes, perovskite. So please welcome Irina.
Thank you very much, Ziv, for introduction, and Ned for initiating the seminar and, you know, inviting me to present here. I'm very, very happy to do so. As Ziv mentioned, I've just started my job at UTS, and like literally in the beginning of this year, so I'm still very much in the organizational mode of setting the lab and purchasing equipment. And my background is actually in studying Phonon. Phonon states acoustic properties and mechanical properties of materials, and I have interest in novel materials, for instance, materials for solar energy like perovskites, as well as very keen on doing research in biomedical area, biomaterials, hydrogels, tissues, cells, etc. So today I will focus purely on solar energy application and perovskite materials. And the information, can I ask if you can hear me very well? Everywhere? Excellent. So the material which I will show, the results and simulations that I show, are all published in a recent paper. And you can see that this paper has 8 authors and 6 affiliations, so it was really a very collaborative project. And myself did Brillouin spectroscopy of perovskite crystals, hybrid organic-inorganic perovskite crystals at Imperial College London, where I did my fellowship a few years, for a few years, finishing last year. And the fabrication of these crystals was done at Oxford and PCI Paris, and the numerical modeling using density functional theory was done actually in Israel in Weizmann Institute of Science. So the whole project took about 2 years to complete and to publish, and during that time 2 of our team members have relocated, me including, to UTS, and David Egger, he has joined University of Regensburg and started his group there. So that's why we have these affiliations also included. So, as Ziv mentioned, I spent some time as a postdoctoral fellow working at Amolf, and that's probably the first time when I got interest in perovskite materials. So that was a couple of years back, and it was a very hot topic back then, and it's still a very hot topic now. And mainly it's because these are the materials which had shown such an improvement in efficiency for solar cells in the last couple of years that the world haven't seen before. So in 2016 there was reached a record of 20%, and now perovskite materials are actually no worse than more traditional conventional silicon or gallium arsenide, and they keep improving. And the advantage or the appeal of this material is that it's fairly easy to fabricate. They can be fabricated from solutions. They can be even sprayed on cells, and the fabrication happens at room temperature. and they are quite soft materials, so you can deposit it on corrugated surfaces, or you can make a flexible solar cells out of it. And for that reason, mechanical properties are quite important. As it stands out that mechanical properties are also very important because for this type of materials, because they have relation to electronic properties. And as I will show on next slides, it has been shown recently that the lattice vibration and the electrons couple, and the lattice vibration influences largely the mobility of charge carrier. So, as well, there is such a variety of different ionic compositions and different perovskites, and the numbers in literature are so diverse. Sometimes they are varying, orders of magnitude. So it would be pretty good to actually clear this out and to show how ionic composition is related, or how by tailoring ionic composition we can tailor mechanical and electric properties of these perovskites. So this is one of the previous studies I want to show you, which essentially very clearly stated the influence of lattice vibrations onto mobility, electrons and hole mobility in perovskites. And there are two essentially reasons for low mobility, and it could be intrinsic and extrinsic effects. So intrinsic effects, they are essentially scattering of electrons or holes on lattice vibrations or phonons. And unfortunately, we can't do anything about it. It's very much specific to the material. And the second one is extrinsic effects, and this is material imperfections, which could be lattice disorder, could be impurities and things like that. And here we can work and we can improve these things by, perfecting fabrication techniques or post-processing techniques, etc. So, but let's deal with first, which is intrinsic effects and the lattice vibrations. And this article, which was published in 2017, have clearly stated that the charge carrier mobility directly linked to elasticity of material, elastic constant C in that formula. I do not have a pointer, but I will. What shall I do?
With the mouse.
I can do the mouse, yes. So you can see, so this is charge mobility, and this is a C elastic constant, and we have direct proportionality. So if we want to know charge mobility for a concrete perovskite crystal or a thin film, we need to know elasticity of this material. And this is essentially what motivated me and my collaborators to do this research. Well, it helped a lot that I was already at Imperial College doing phononic research, and I was measuring phononic properties of all sorts of materials. And a friend of mine who works as a lecturer at Imperial College Chemistry and part of Organic Electronics Center there, he has a keen interest in perovskites as well. So we've decided that we've taken a bunch of different perovskite crystals, and they will have slight variety in terms of their composition. So you have here methylammonium lead chloride, bromide, and the mixture chloride bromide. And we could also substitute a cation, so the organic molecule here, from meldinium, and obtain from meldinium lead bromide. And thus we can essentially change X site, which is halogen atom, or A site, which is organic molecule, and see how it affects mechanical properties. So in my talk, I'm going to briefly go through fabrication and clarification of the mixture composition. Then a little bit more deeply in brilliant spectroscopy, because that's actually was my part, and you know, I might not be able to tell you some intricacies of fabrication, but I definitely can tell you about brilliant spectroscopy and microscopy measurements. Then go into numerical simulations using density functional theory and discuss the results. So let us start. So these are very faint pictures, but nonetheless, I hope you can see there are these crystals here. So these are our perovskite crystals. They're a little bit fainter than I would expect, but these are likely to be chloride crystals, and they are indeed transparent for visible light. That's why they look so clear. And the crystals were methylammonium perovskites, were fabricated in Paris by Zhou Chen, and Fa from imidinium crystals were fabricated in Oxford. So nonetheless, inspired the differences in locations, they were made approximately the same, in the same way, I mean fabrication technique. So they were prepared out of solutions and then kept at elevated 55 degrees Celsius temperature for 12 hours. The crystals formed and then they were dried under the vacuum, and we obtained these beautiful crystals. They lie here on millimeter scale paper, and you can see that they roughly, so the lateral dimension is about 1 millimeter, so we can say that they're roughly a millimeter cube in volume. And they were, depending on composition, they were varying from very faint transparent for chloride crystals to very bright orange reddish to bromide crystals. Okay, so we have these mixture crystals, and initially Zhou has used a recipe to fabricate crystals with about 15% of bromide. And when we obtained the crystals, they looked quite yellow. So we were wondering what went wrong in fabrication process, and we did need to prove and to find better what percentage of chlorine and bromine are in these mixture crystals. So for that reason, she did X-ray diffraction and looking at the peaks X-ray diffraction for pure chlorine and for pure bromide crystals, and then for the mixture we were able to feed and obtain concentration of chlorine and bromine in the mixture, and ended up with roughly 16% of chlorine and 40% of bromine. So let's now go to Phonon measurements, Brillouin spectroscopy measurements, and before I start I would like to actually ask a question. Is anyone familiar with Brillouin spectroscopy and Brillouin light scattering in general? Yay! Hooray! We have a couple of hands. But I thought I'll prepare a few slides because usually this is the least known technique, and I would like to spend a few minutes to familiarize it for you. And so it's a measurement of mechanical properties, or you can actually reconstruct the whole tensor of elasticity using Brillouin scattering and Brillouin spectroscopy by using light. And it sounds counterintuitive how you can use light to measure mechanics, but in the end it's about interaction between light waves and sound waves. And so happens in the regime where sound waves are high frequency waves, so there's hypersound waves, gigahertz waves. It happens that the both things actually have roughly the same spatial dimension, so they can interact and they can phase match. And that's what happens in the process of Brillouin light scattering. So the light, the photon interacts with pressure waves that are intrinsic pressure waves due to thermal pressure fluctuations in material, and the scattering happens. And this process is phase matched and energy matched, so goes with energy conservation. And what you do get here, so the incident light comes in, meets with an acoustic wave, gets scattered, And because the acoustic wave is a moving wave with a speed of sound, so what happens is that the scattered light loses a little bit of energy or gets a little bit of energy, and this results in a frequency shift. And this frequency shift exactly proportional to the acoustic wave frequency. So what acoustic waves we are talking about? Well, there are plenty of different acoustic waves, but in the bulk materials we usually have longitudinal waves, which are a little bit like an accordion, so densification and extension of material, and there are a transverse or shear waves, as we call it, so that the material sort of moves perpendicular to the propagation direction. And to distinguish it very clearly from Raman scattering, so the waves I'm talking about, they're collective motions of particles. They are not vibrational rotational states of atoms and molecules. So the Brillouin scattering happens at very low frequencies, gigahertz frequencies, and Raman at terahertz frequencies, optical frequencies. So let me give you, it's perhaps the only slide with mathematics and expressions here, but nonetheless, so due to energy conservation and phase matching, we can obtain expression for a Brillouin frequency shift, so that's the shift which scattered light inherits after meeting with acoustic wave, and this frequency shift is proportional to the speed of sound, depends on scattering geometry. There is this cosine of theta here, and there are a few properties of light, which is wavelengths of light and refractive index inside the medium. So, but you can see that by obtaining the Brillouin frequency shift, we can actually directly find out the acoustic speed of a certain wave. And the crystals that I showed you before, perovskite crystals, they are not isotropic, they actually have cubic symmetry. And in cubic materials, in materials with cubic symmetry, we have 3 different acoustic waves, and these are quasi-longitudinal, quasi-transverse, and pure transverse. So we would have 3 acoustic speeds, and we have 3 different elastic constants, and it's all governed by a Christopher's equation. So finding the speeds, we can find the constants, and we can calculate the elasticity. So let me take you through the measurement setup. So as I mentioned, the measurement was done at Imperial College London, and this is a very, very minimalistic scheme of the setup. So we have a laser, and it's a single frequency laser at 670 nanometers. And this laser essentially goes through a lens and through a beam splitter, and then reflects here in a mirror. So this is sort of like a microscope arrangement, and focus through an objective into a crystal. The scattered signal that comes back from the crystal, we are working in a backwards geometry, traces the same path that incoming light also reflects here at the mirror, comes to a beam splitter. And because we have this quarter plate here, the polarization of the scattered light is 90 degrees off compared to the incoming light, and it gets reflected rather than transmitted through this polarization beam splitter, and we collect it and filter the signal and analyze it in a special Bild spectrometer. So the special Bild spectrometer is actually quite a simple device, which is called virtual imaged phase array, and it's nothing else as a Fabry-Perot, which is put on slight angle, about 1 degree, and has coatings on it. So it has a transparency window here, and it has complete reflection coating here, and a little bit transmissive coating here. So it takes all of the light, and then it disperses it on angle with regards to the frequency of the light. So what you end up with diffraction orders And for each order, you would have an elastic peak, which is relay scattering, the scattering at the same frequency as that incoming light. And you have these new peaks next to relay, which are called Brillouin peaks, which are frequency shifted. And the frequency shift, as I mentioned already, proportional to the acoustic velocity. Okay, so that's how spectra look like. And let me first talk you through this left graph. So, as I mentioned already, we have these diffraction orders, and what you can see here is actually just between two diffraction orders. So this is, say, 0th order relay peak, and this is 1st order relay peak, and this is all of the new information, so these Brillouin peaks that we get in between. And you remember that we have Stokes Brillouin peak and anti-Stokes. So Stokes is light lost its energy, and anti-Stokes peak, light which gets a little bit energy from acoustic wave. So we have all sorts of little peaks, Brillouin peaks here. So this, for instance, is longitudinal, corresponds to a longitudinal acoustic wave, and it's Stokes peak. So it corresponds to this high order diffraction, and Stokes are on the left-hand side because we lost the energy, and anti-Stokes are on the right-hand side, and we have also two little peaks for transverse acoustic waves. So analysis of this spectra takes a little bit of time and experience, but nonetheless it's fairly straightforward. And we've done the spectroscopy measurement for all of the crystals, and that's how it looks like. And what you already can see that, well, Brillouin peaks are much smaller than Rayleigh, that's for sure, but there's nothing surprising because Brillouin scattering is not a very efficient process. And secondly, what you can also see is that the location of each peak for each crystal is actually unique. And that's because elasticity for each crystal is unique. It corresponds to a atomic lattice of this crystal. So what we also did, and which is a very important point for doing Brillouin spectroscopy, especially because the crystals have cubic symmetry, is to align the crystal along a certain axis, because you can imagine we have all sorts of direction in the crystal, and the speed of sound actually will depend on direction of the acoustic wave inside the crystal. So what we did, we tried to align it along a principal axis, so one of the sides of this cube, and we've taken the spectrum, and to check that we indeed aligned our crystal along principal axis, we turned it 90 degrees. Since it's a cubic symmetry, then changing a side doesn't actually make any difference, and we confirmed it with measurements. For 90-degree measurement, we obtained rather similar spectra. The variation was within the measurement error of 100 megahertz, and we were quite happy with that. Okay, so let me talk a little bit about the numerical simulations. So, okay, we've measured these crystals. We obtained results. They were roughly within the range of parameters published in literature, but as I said, the literature actually presents a lot of different information and different measurements with different techniques, and the numbers scatter quite a lot. So what we really wanted to do is to simulate these crystalline structures and to verify our measurements using numerical modeling. And so happened that our collaborators at Weizmann Institute of Science developed this very neat DFT calculation, and they've have huge experience modeling perovskite materials in general. So this calculation essentially allows to calculate the crystalline structure from the first principles and obtain potential energy, and then obtain elastic parameters and potential electronic properties as well. So here you see a calculation for MA and FA crystals, and then using using perturbation theory in the same calculation package. The package is developed. It's a open source program developed in Vienna and available for everyone. You can calculate elastic constants. So, and this is a result of calculation. So you see our 4 hero materials, and these are the 3 acoustic waves that we expect to obtain in these materials: quasi-longitudinal, quasi-transverse, and transverse. And the frequencies that we've measured in experiments, Brillouin experiments, you see there are some missing fields here, and these were peaks which were too small to reliably fit and obtain a good measurement for them, and they're usually for transverse waves which not very well couple in the scattering geometry. But nonetheless, we were able to obtain some speeds for longitudinal and transverse waves, for instance, for MA-lead chloride and FA-lead bromide. And these are theory calculations, and David and Ido, who did calculations in Israel, they've been very careful and run calculations for different directions along three principal axes. What you see here is that the numbers are different, and I mentioned that if it's a pure cubic system, then the numbers should be the same. But in fact, it was very hard to do a realistic calculation, so they had to do an approximation and fix the orientation of a cation molecule. So organic molecule orientation was fixed, and therefore the cubic symmetry is broken and the speeds are slightly different. But what we can see is that the agreement between theory and experiment was actually pretty good. We were surprised how close the numbers came together, and we got in fairly good agreement with the published literature on the same crystals obtained by AFM nano-indentation measurements and by Brillouin measurements as well. So, yes, this little blonde paper published in 2016, the French group, they've done Brillouin scattering, neutron scattering, and I think something else. So how we can explain, how we can now connect the ionic composition with our results and what we've measured. And I would like to give you a little bit of explanation and how we understand these results. So essentially, let's look first at substitution of X side, which is halogen atom. And we go from bromide crystal through the mixture to chloride crystal. And that's what our data is showing. So the yellow one is experiment, the red squares is theory, and the blue is, the red one is average theory, and so across all directions, and the blue one is theory. So the agreement is there, especially with the theory along the principal axis 1, 0, 0. And what we see is that bromide, MA-lead bromide, is softer. It has lower acoustic speed and lower elastic constant. And chloride crystal is much harder or stiffer, as you wish. And it has higher acoustic speed and it has higher elastic constant. So what we also know about this range of crystals is that they have different ionicity. So electronegativity of the lattice is different based on the halogen atom. And it actually also means that the unit cell of the lattice is slightly different as well, right? So in bromide, the unit cell is larger, and in chloride, the unit cell is smaller. So what it means that the stronger electronegativity, the smaller the unit cell for chloride, the larger the acoustic speed and the larger the elasticity. So it seems that the lattice is more compact and everything is tight closer together, and you know, electrostatically it's like a more stable structure. So good news that the mixture came somewhere in between. That's where we expected it, and that's where we got it. A little bit untrivial result is for substitution the cation organic molecule. And on first sight, Fa molecule is actually more symmetric compared to Ma. But what the energy calculation have shown, and you can see it from here, is that these energy maps, and you have lines here which are isobars, which are the lines of constant energy. So this picture looks much more symmetric, and I hope you agree with me, than this one, especially around this hydrogen atom here. And so this is for Fa, and what happens here is that the energy, potential energy, and around this Fa organic molecule, it sort of spreads further and interacts more with halogen atoms, and reduces ionicity of the lattice. And as a result, we have much weaker elastic constant for Fa crystal compared to Ma. If this explanation, it makes sense to you, but if I'm happy to take it to discussion after I finish the talk. So essentially the symmetry of potential energy, and the fact that the potential energy gradient around organic molecule methylammonium is more compact and interacts less with the lattice, means that electrostatically it's a stronger configuration, and so happens it also has a high elastic constant, higher acoustic speed, and it's more stable, and it's stiffer. So which was completely we didn't expect it at all, and it doesn't come from just analysis of the two organic molecules. So, and the last little bit of discussion that I want to give is about elastic anisotropy in these crystals. And it is quite usual for longitudinal waves to be faster than transverse waves, but in perovskites they're quite some faster than transverse ones. And if you take, for instance, so this composition, crystal composition, then we find that transverse wave is only 44% of longitudinal, and for Fa composition we have 62%. So it's been also indicated in previous literature, anisotropy, elastic anisotropy, which means that these materials are quite susceptible to shear movements, and they actually, some of the authors do say that there are dynamic rearrangements can happen, and they're quite soft for shear stresses and shear movements. So I hope I did give you some new information and some new insights in perovskite crystals, but I wanted to elaborate a little bit on what can come from this work and some other interesting aspects that we, for the sake of time and not having maybe right setup, we're not able to do it. And of course it would be nice to connect this study to actual measurements of electron and hole mobility, charge mobility, and study electronic properties for the same crystals. As well, a very important issue is exploring the line widths, because so far what we've done, we only calculated where the peaks are located, but we didn't study the line widths, and that's because we didn't have enough resolution in our spectroscopy system to resolve the line widths properly. And what we did, we just fitted it with a Lorentzian curve, assuming a harmonic oscillator model, but it's actually very far from the truth, and there are many reports saying unharmonicity of these lattice vibrations, and that the peaks are not Lorentzian. So it would be very good to study some dynamic effects and anharmonicity, provided a system with high resolution. And the last one is temperature-dependent studies. So these crystals, they go through phase transitions from cubic to orthorhombic configurations at actually almost at room temperatures. And it would be very good to do these studies in a temperature control environment and see how elastic properties change through the transitions. So at UTS, where I'm starting and building my lab, so I will be setting up a Brillouin microscopy and spectroscopy system, and the system will be specifically targeting some of the open questions here, so it will have much higher resolution than the system I used to work at Imperial College, and it also can do not only backscattering geometry, but also 90-degree scattering geometry, so it allows to measure these transverse shear waves much better. And I hope to answer some of these questions in the future. And thank you very much, and I look forward to your questions if there are any.
I noticed you haven't done the measurement on iodide perovskite. Iodide perovskite. So you only have.
Yes, that's right.
So
yes.
is it because it's not cubic at room temperature?
No, the answer is very simple. We actually did have these crystals, but we couldn't measure them. They were absorbing at 670, and yes, so essentially they were steaming. They were absorbing everything.
You can't change the excitation.
You can change the excitation. Brilliant scattering happens at it's frequency independent. But so happens that our laser, we didn't have a longer excitation laser. So that was a problem. You need to go to near-infrared for iodine because it absorbs everything invisible. So they're quite dark.
So basically you can do it.
Yeah, you can do it. Yeah.
Because iodide is not cubic structure.
Yes, but that's not the problem. Yes, the equations, reconstruction equations will be somewhat more complex, but provided you know the axis, how you send light and collect your acoustic wave information, then you can still do spectroscopy.
Another question is, I know you need to have a proper alignment.
Mm-hmm.
So single crystal is very important for this measurement.
Yes.
Is it possible to do to measure the thin film?
Thin film. So it will have domains of different
but
symmetry.
Now the high quality thin films, they have a sort of preferred orientation.
I see. Well, I guess it's always one way to find. Let's try, and then we find out. But I see if there is a preferred orientation, then you will see it. You will definitely be able to get information of this orientation and align with this orientation. It might be that the peaks will be broader if, for instance, so we are talking about interaction within a focus volume, so where the light interacts with acoustic waves, and if there are different domains of different orientation, they will all send scattered light that you collect and analyze, which leads to peak broadening. But that's the only issue that might be. So it might not be that clean, the results, but nonetheless you still get some information.
It's very interesting, very interesting in general, but the difference in mechanisms between the varying the organic component and varying the halide was very interesting. So the symmetry argument for the organics and the stiffness of the bond essentially with the halides. What do you think you could say about the relevant or relative contributions from the halide and from the organic species in in determining the elastic constants? And does it vary depending on which of the acoustic phonons you're measuring?
That's awfully a good question. So we haven't done like the differentiated studies per se, but I try to see what I can say from our results. So what I can say definitely is that changing a cation, changing organic molecule, actually doesn't change that much elasticity, you see, but there is a quite a big difference. I think it's a little bit bigger, changing halogen atom from bromine to chlorine. It's a bigger gap.
That would seem to make sense, yes, because that's the halide's to do with the bond strength, essentially, and so that's going to be changing much more dramatically than the symmetry change in the organics. I guess the combination of the two can make a very big difference.
Yeah, so and that's you can see, for instance, from neodymium crystal and the first one, the top one, the difference is substantial. It's like more than 20% in elasticity, and it would affect by 20% charge mobility as well. So then you can draw some recipes how to improve charge mobilities based on that.
Another question? So that's good. We have class after us. So let's thank Irina again.
Thank you very much.